what I'm going to be talking about, they keep talking about address depletion, but we have network grade NAT systems that are actually taking care of things pretty much. But as I was explaining to someone earlier today, when the first IPv6 network came up, I actually set one up. This is back in like the 80s, right? So we set it up. We're so proud of ourselves. We pinged each other with a V6 ping, and we did a V6 trace route, and that was all you could do, so that was it. The next time we set up a V6 network I was with a bunch of network engineers, network scientists, and network operators. And we set up V6. It was real easy to do. One major problem. A third of us set up the network, and it was so open you could drive a Mack truck through it. So from a security standpoint, it was a nightmare. I was one of the 1/3. So I said, this is crazy. Because actually, back in 1985, we developed a protocol that was actually better than V6, and it got shot down. There's politics. A guy from IBM Zurich called it electropolitics. Fine. So I wanted to come up with something that didn't disable current information security systems. Well, I was a network scientist. Came up with 128-bit V4, IPv4. But it had all the problems of V6. Fortunately, I had a friend who had network operators for friends. And they chewed and he presented it, and everything that they were irritated with, he took out. So we wound up with this thing that I'm going to be talking about now. And V6 has been coming since 1988. Oh, I went to an IETF meeting, and V6 was introduced. And you know what we did in order to test out the network protocol? We gave each other logins on our personal machines. How many think that's a good idea? Back then it was, because you couldn't do anything. What changed the internet? Does anybody, you almost have to have gray hair, remember Mosaic? Mosaic was the great-grandfather of Netscape, Firefox, Internet Explorer, Safari. Once that happened and the internet was easy to use, it changed the game. I was at Bowman Gray School of Medicine where that happened, and we had an Ethernet network that collapsed probably once a week because of the use on the internet. And it was never like that before. So the internet is actually commercial. It's an information source. It's important for academics, for everybody. So the game has changed. In fact, what's interesting, well, we'll get to that when which one is it? Oh, it's the ENIP for IEEE Chat, Chattanooga. That one there. PowerPoint. And I actually put this in PowerPoint format. I figure who can't use it? Now Windows 10 doesn't like PPT. They like PPTX. Yeah. There we go. And all I need is a space bar, and once you put an F4, is it ready to go?
It's ready to go, sir.
Okay, so one of the things we did, IPv6 has the way of being like Arnold Schwarzenegger in Terminator. You know, you will use V6 or I'll be back. You know, that's not how you deal with human beings. So that's one of the things we didn't want to do. If it's working, don't break it. If you don't want to use it, don't. And that was one of the things my buddy found out. And oh, by the way, once I gave him the idea, he coded the thing in 3 weeks. So what we're going to see is what happened from 1992 to 1994, some of the V6 challenges, and then we're going to talk about ENIP. Now, interestingly, because I'm trying to get this standardized, I went to the guy that did NAT. NAT took the industry by surprise. I actually talked to the guy that did the NAT, and he says, you won't be able to do what I've done because they didn't know how to deal with me. They know how to deal with things like this now, so I'm going to have a little more difficulty. There were a lot of different protocols coming, realizing that the address space was going to be an issue, and these are a bunch of them. Actually, I did my thesis, my PhD on OSI Layer 4, and I also worked with the medical community doing DICOM, Digital Image Communication Protocol. And I'll never forget, there was a French guy from Boeing goes, TCP/IP will be dead. It is no longer a good protocol. It will be gone in a year. And what happened? OSI was gone in a year. And so luckily, when we did the DICOM protocol, I said, humor me, give it a hook for TCP/IP just in case TCP/IP is still around. And so that's the story with the digital image communication. Okay, so what this is talking about is different ways of increasing the address space of IPv4, all of these protocols here. And let's see if we... Now when we get to the IPv6 problem, see all of the things on that billing system, handset, management interfaces, DSLAMs, routers, traffic management boxes, load balancers, all these things have to be altered. And anyone's dealt with a big system and done risk management, there's a probability of failure associated with each one of these. And it is multiplicative. So basically, it's dangerous is the bottom line. And so when we set up that V6 network, I was one of the ones that won, and it worked. Everybody's V6 network worked. Just some of them where you could drive a Mack truck through. Now this is something interesting on the V6 deployments. I didn't really realize this, and again, the network operators did. And when you do things like the border gateway protocol, peering issues, these all have to be negotiated between all of the ISPs in the world. Very onerous type of a thing. So again, what my good friend Sam Patton was able to find out is that the operators don't want to have to do that. They'll do it if they need to do it, and if they don't want to do it, they don't want to do it. So the first thing I came up with was 128-bit IPv4. You can do it. There's one big problem. It is as insecure a protocol or causes as much security problems as V6 did. And it required major changes. So when my buddy talked to his friends that were network operators, he backed out things that would make it difficult for a network operator to use and to make things voluntary versus mandatory.
Can you provide an example of some of those challenges to network operators?
For network operators, well, like the BGP peering type of things, with the V6, okay, you do V6 and I do V6. And it's almost like Dirty Harry. I know what you're thinking, punk. I can do V6, but can you do it right? Well, can you, punk? And so if you do it badly and I peer with you, I've opened up my network to problems. Right now, people roughly understand security issues with V4. V6 opens up a door for a bunch more. I went to anybody been to a Black Hat conference? Good. Black Hat is a conference where they basically whack machines, but fortunately, they show you how they whack it and they show you how to fix it. So and before they go to the conference, they go to the vendor, say, you know, if you fix this, I'm going to show how bad it is, but if you fix it, I can say you fixed it. There's a cheaper one called ShmooCon, and it's about, instead of $2,000, I think it's like $200 or $300. Same thing. But I went to one of them and said, do you have V6 turned on? And the guy at Black Hat said, are you kidding me? So those are guys that actually, you know, make their games by doing these types of things. The other thing, has anyone ever looked at a V6 address? They are nasty to look at. Most people are used to the address up there. So what we did is catenated two V4 addresses. I can look at that and understand what's coming. The first four is what's called a network address. I can recognize that. The second part of the address is actually the old-fashioned, out there, private address space, because we didn't want to break anything. So you can still use a private address space. You don't have to use this. If you want to use it, you can. You choose to use it. But I can read that. If you've looked at the V6 addresses, they're a lot uglier to look at. So again, the 65.127.221.1 would be a routable public address. And that's the beauty of this protocol. Because you have that as one of your addresses, all of your firewalls work. All of your IDSs work. All of the different equipment that works. The second half of the address is the additional address if you need additional address space. So you'll use the private address space as the concatenated. So instead of getting, I forget what that it's only 16 million times more addresses. I think it'd be something like 20 or 24 million if I allowed all octets. But I didn't want to break private addressing so that people that hated this idea don't use it and everything works the way it's working today. And there's the host address, which again is the private address space. Okay, so here's another thing. When I went to Internet 2 and described this to the people at Internet 2, I said, well, what we're going to do is you have a enhanced IP node, and then you have a NAT. And the person at Internet 2 would like to bite my head off when I use the evil word NAT. They don't like NATs, but I said, this is stateless. And their jaw dropped. It's a stateless NAT? Then they were interested. Why? Because with that, I talked to a fella at actually one of the Black Hat, said that he could put my protocol on a daughter chip on an Ethernet card because the protocol is simple. That's why. Not that you'd want to do that, but it's to let you know you could put this on one of your ports on a router and have enhanced IP running on that particular port. And I'll show you hopefully. Oh, how much time do I have?
Oh, you got plenty of time.
Good, because I'd like to show. Anyone ever heard of OpenFlow? This is going to be a treat for you all because it's an amazing protocol. And OpenFlow with this can do some really amazing things. Okay, so again, because of what my buddy found out, we wanted to minimize change. We did that. It doesn't replace existing protocols. We don't want to break anything. But we use the option field. It was interesting. Anybody know who Vint Cerf is? Vint Cerf basically is one of the people that invented the internet. It was ARPANET at the time. But I talked to Vint Cerf and I told him what I was doing, and he goes, I knew it was a good idea to have options. But he is a V6 person right now because he wants to be able to, address the stars in the sky and stuff like that, thinking really big. I just want to solve networking problems. But, and that's a big thing. The stateless NAT is a very big thing. And we only add 12 bytes. If you ever, we'll show the format of the protocol. Here's your typical IPv4 protocol header. Anyone that's done network programming is very, very well, they know this. Here's the additional things we put. The option ID. So it's got to have an option. The option length, how big it is. And then this ES is enhanced IP source present. EDP, enhanced IP destination present. And the bottom one, extended source, that's what they're talking about. So if ESP is set, there'll be a real address in the extended source address. If EDP is set, the extended destination address will be set. So those are the only things we've added to the protocol.
Excuse me.
Yes?
In the header you just gave,
Pardon me?
the header for IP units, you get the header for quality of service?
For what?
QoS, quality of service.
QoS is part of an additional packet when they want to go to the QoS. That's one of the things. Oh, I did a protocol called Express Transfer Protocol. It had a 32-bit quality of service field, and it was gorgeous. But anyway.
The question I asked, the reason I asked because in the header, if there's no quality of service on the packet to say this is voice or this is let's say a real-time event, it's a phone call. So as you route this packet, you have to be prioritized because when I say, hey, how are you? I don't want this packet to arrive 2 days ago. How do you know that?
Well, typically it's in the TCP header. This is just the IP. And TCP will be talking about those types of things. And the other thing too is wait till you see what OpenFlow can do for you with regard to quality of service. And actually, what do you call it? The people up in Wall Street are using this because if I can make a trade faster than you, guess who wins? And so they're very, very interested in quality of service. So you'll see in the next presentation how you can basically address your types of things with various levels of quality of service, depending on how much you want to pay for that bandwidth, and how to more successfully use the bandwidth available. Because has anyone ever heard of an elephant flow? An elephant flow is a transmission of such great quantity of data that because of the TCP protocol, you will in essence DOS a system, denial of service. You're not doing it on purpose. It's just a huge amount of data, petabytes. So there is a way to identify an elephant flow and throttle it so that not at the TCP level, but at the IP level, bring it down so that you're not choking, well actually layer 2, you're not choking your internal network. And there's a way to do that. I'll show that in the next. See, fragment header, flag identification, protocol time to live. I may be wrong. I don't know off the top of my head whether it might be IP where the quality of service is there, but it's only 8 bits. You only have 8 bits for quality of service.
It's layer 2 or the IC model. The IP is on layer 3.
Yeah.
Layer 1, layer 2, layer 3, and then the next one is
It's 4.
Transport layer with TCP or UDP. With IPv6, the version 6 of this, on the IP level, the header will let you know the quality of service, element, if this is a voice or it's data, it's routers, the security is embedded. So I'm trying to see how is this better.
No, the reason it's better is you do everything you're saying with an insecure network. And again, it's like Dirty Harry. Well, do you feel lucky? Well, do you, punk? I mean, you're putting your network, it will do what you say. But my question is risk-benefit. Everything you do in life is risk-benefit. Okay, now you have a benefit there. How big is the risk? If the risk is here, I don't want to use it. And in my opinion, the risk is up here. The benefit, and when you see this open flow, especially with the types of thing with quality of service, you're not going to need it. Everything's got its issues, everything's got its risk and benefit. The next thing you'll see. So yeah, V6 has a lot of stuff in it. What they did is say, oh, V4 stinks. And how did V4 get here? V4 got here because there was a thing, I'll think later on here, called the Network Control Protocol. And they went from the Network Control Protocol to IPv4. You know how they did it? On one day, they turned off Network Control Protocol. The guys, when I went to the IPv6 meeting, they were planning on doing that, just turn off V4. But what changed the game was Mosaic and the fact that industries, normal people, businesses were starting to use the internet, whereas before it was just network engineers. And you can, like they turned off NCP, no big deal. They were all research scientists, and they fixed it. You don't just turn off V4 and expect it to work. So the problem is this interface of the two protocols. That's your difficulty. And has anyone dealt with V4, V6 rather? You have. Have you dealt with ISOTAP? ISOTAP is one of the ways of getting V4 to work with V6. We looked at that protocol. You know what we nicknamed it? Is a tap. You want to own someone's communications? Yeah, hopefully they're using ISOTAP. And then I'll tap right into them. See, it's the security issues that motivated me for this, not operational issues. Again, risk-benefit. I saw the risk through the roof. The benefit was marginal, was my opinion and the opinion of my friends. So anyway, this just basically shows how the protocol changes. Initially, and this is one of the cool things, initially the host doesn't know where it's going. And this is where, like when we get to OpenFlow, it's amazing what you'll be able to do. Once it hits its NAT, you, as the system administrator, determine where a host connects. Where the host connects is the routable public address that it will see. And you'll see with OpenFlow, it's amazing what you will be able to do. So initially, it doesn't know where it's going. See, so I'm going to transmit this from the enhanced IP1 to its stateless NAT. So this is what changes. I started off as 10.1.1.2. You notice now that's my extended address. Once it hit N1, N1 says, I'm your NAT, and it sticks its address in there. It doesn't cache it, doesn't have to cache it. It's stateless. Boop, there's where it is. You knew that you were going to the other side, so you see 65.127.222.2 is the network address, and the host address is 10.332. We're all ready to go. And when it sends, N2 sends it back down, it changes the header as you see here. And oh, by the way, anybody, if anybody, at the end, enhancedip.org, these presentations are there. So you can go ahead and look at the presentations there. And this is basically how the Other thing, we didn't want to break what's working. There is a v6 DNS request. It returns 128 bits. We only want 64. So we call it, instead of a AAA return, we call it a AA because we just toss the remaining bits in the toilet because we don't need them, the other 64 bits. So you see how nasty an IPv4, IPv6 address looks. They're ugly. They're really ugly. It takes a lot to get used to them. After a while, you can sort of read them. But you'll see how this changes. But that's what it actually is going to be returned. And you see the readable version. I mean, I've been dealt with networking. I can read the bottom one a heck of a lot better than I can read the top one. And the other good thing about this is, let's say for argument's sake you have either, let's say your Volkswagen and you have your production line is there. Some of the information you don't care if people see. Some of the information you do care, and some of the information is actually the things that operate your machinery. The things that operate your machinery, I don't want it on the internet. The stuff where you can tell what I'm doing, I might like corporate in Germany know about, and some other people and your supply, your dealers know about. And so that would be two separate network addresses. One to go to corporate, one that would only go to your dealers, and the third one is just an internal network, is how you do it. So the first two would have a network address. That very last one would only have an internal address, would not go to a NAT, would not be enhanced IP, because I don't want it to be routable. It's for the factory here in Chattanooga. Okay, this is the thing that was amazing. My buddy coded this in 3 weeks. I was stunned because it's relatively simple. It added only, doing Linux is how we're doing it, 200 lines in the kernel. And then, like you see the numbers. It's not a lot of code. IPv6 is 600,000 lines of code. It's got something like 900 RFCs to explain to you how to set it up. And that's one of the reasons. You can set it up, but how do you set it up correctly? I saw one network set up very well, a v6 network. They had 3 PhDs running it and setting it up. How many small companies can afford 3 PhDs? Or 2? Or 1? And it is that difficult. To set it up's easy. To set it up correctly, that's the trick. And in fact, one of my friends at Georgia Tech, I don't know if he ever wrote, I don't check to see if he wrote this thing, but believes that a IPv6 firewall is NP complete. For those people that don't do computer science, that means it's impossible to do. It might be NP hard, which means maybe you can do it. I don't see how. It's because of the complexity. And the complexity is this. v6 loves to give you addresses. It really wants to help you get to the other side. So if I have 5 addresses or 10 addresses or 16 on my machine, and then I have to write a firewall to each of my destinations that could have anywhere from 1 to 16 to 32 addresses, think about doing it. It is very difficult. Impossible? I hate to use the word impossible, but difficult? Yeah, I will say difficult. And this is just basically one of the socket in, how it would work. You notice there's an addition of the additional addresses at the bottom down there. And that was just one of the lines that you had to do. One of the difficulties is, we call it, what do we call it? A stub code. Because what we do is we do an IPv6 call and throw away 64 bits. So that's not in the kernel. So we had to add that. And that's one of the additions we had to do. Ping at present doesn't work because we weren't that interested in doing it. The experiments were between sites we know, so ping would have to be done. Not that it's impossible, we just didn't feel like going around to do it. Let's see, and these are just the ways to manipulate it. Everything we've tried so far has worked. We haven't found anything that hasn't worked. This would be really cool, like the person from Chattanooga State, to test this thing out. If you go to enhancedip.org, they actually have VMs, so you can test it in a VM environment, break it, rebuild it, no big deal. The code is there too. The code stream is there also. And what I'm doing right now is I'm building My buddy built it for me, an enhanced IP router. I'm going to build my own home router. Once I get good at it, if you want, I can take it to you all, and then you all can start building these things too. What we have to do, though, is get with EPB, because you have to allow options. What typically happens, well, I think we're going to get to that in here. I guess not. Enhanced IP, this is enhancedip.org is where you get all of these. And, if I get this, I might be able to show you. But there was a live demonstration of this thing working from the University of Delaware to Maryland. What I need to do is get EPB, if they turn options off, just let options go through, I'll be able to connect to the network at Delaware and Maryland. So my idea would be really cool, like with Chattanooga State or UTC, whatever college wants to do this, is to get it working locally, test it out, and then maybe move out from here to maybe Nashville, then move around to the state of Tennessee. This is somewhat melodramatic, but it'd be so cool if we did this and it actually took. Then it would go down as Chattanooga Saved the Internet. That would be cool. But that aside, to test it out, and I'm going to show another presentation here. I think this is the last slide. Yeah, I'm going to show another presentation. Let's see. And this is OpenFlow. For those that, come on, please work. Yes. Did I get it? I failed. Fat fingers. How about that? Yeah, there we go. F5. Come on. There we go. There we are. Okay. An introduction. No one's heard of OpenFlow. Typically, here's how it worked. What's interesting is way back when, in the 60s and 70s, what they did is they had a controller that controlled all of the nodes on the ARPANET. It wasn't the internet. It's called the ARPANET. That's how they did it. And then Cisco came around and said, wait a minute. If we put the smarts in each switch, we can distribute it better. It'll run faster. And so that happened all the way until about 5 or 6 years ago, until someone said, wait a minute. If we take all of that smarts out and just make it hardware with just a thin layer on top, we can sell each switch for about 1/4 the cost. And so now we have a thing called OpenFlow. The smarts then was taken out to something could either run on a computer, could run on a VM, could run on a cloud, or could run on hardware, but it controlled the switches. Now what's so cool about this is, and I actually tested one of these out, it was so cool. It was called Network Protector. So if it catches a bad site, you can do one of 3 things. You can just toss it, throw it away. You can send it to an instrumented network. You can send it to the sandbox. But what's so cool, you could also send an email firing the person that went to that site. I mean, you could actually send emails and stuff also. So that the actual controller controlled the network, but could also do these other crazy things. What was cool about it is, if a network was questionable, if one of the sites was, without anyone touching it, see, that's the whole idea, zero touch. Without anyone touching it, it would go send it to a sandbox or instrumented network, and would send like an email to a network operator, because they knew to go into that sandbox, so something bad might be happening. A good example of why you'd want to do that, let's say Mr. Lee, is that your name? He just invented, it is so cool. Everybody wants it, right? So something's coming and it's looking like a DOS. So they send it to the sandbox and say, wait a minute, everybody wants to buy that. Let it go, let it go. Then they'd have to put in a whitelist saying, no, not a DOS. We're actually making money. So you can do those things too. And so that's what OpenFlow basically allows you to do. Let's see. So what you have on these is a thing called a northbound application. That's the smarts. And the way they run this thing is all the switches talk to that. But it also talks to a thing called a northbound application. What can it be? Malware detection. It could be business detection. It could be VoIP detection. It could be something like a YouTube kind of things. It could be, let's see, what would be the other one? Fortune 500 companies, big business, and now that northbound app would say, this is Fortune 500, they're paying 3 times more than anyone else. They get this groomed network. I'm doing VoIP. Don't put it on the same network as YouTube. Put it on a VoIP network, and now I need less bandwidth in order to do VoIP or teleconferencing. And you utilize your bandwidth a lot better. So they have things called flow types, and there's different ways Okay, so basically you have, again, the northbound apps talking to the controller. The controller controls the switches. And the switch is just stupid. They basically mirror their ports and send it. One of the mirrored ports is up to your various northbound applications, and another one goes to your northbound app. But the northbound app also talks to the switches and tells it what to do, and you'll see how that works out. But now I'm going to add enhanced IP. Okay, do I need to press that again? Yeah. So let's say you have a malware detector. It's connected to your OpenFlow control. Now, big thing on OpenFlow, if any of you do this, please use secure SSL. It allows you to secure the connection between the controller and your switches. And if you're not going to do that, at least have it an out-of-band network. Not its own VLAN, an out-of-band network for security reasons. So you can do this. Okay, so you'll have, in this, you see I have a tsunami detector, and that's one of the elephant flows. And then the VoIP, there's your VoIP thing. And you could, in addition, you could have teleconferencing. Okay, let's see what this one's doing. Okay, so we're connecting the switches, and you have a top of the rack switch, which you'll, in a typical arrangement here. Sure. All of these, well, actually that VoIP, there's a very light blue line. So each one of these northbound applications have SSL secure connections to the controller. The way it works is, you'll see later on that each of these switches, when they get information, they talk to those northbound apps. But once, let's say, you've identified badguy.net as a bad network, it just sits there doing hardly anything because it's already identified it. Where these guys come in is any new flows get sent up to the northbound application, otherwise it'd be too busy. Okay, and so in this case, here's the nice thing is, once you know you have an internal bad one, what you will do is put a very draconian firewall there to make sure that if somebody in your thing is accidentally, some stupid thing they did, they've messed their machine up, it goes there, it goes to a very draconian firewall, so it won't report to bots. If it doesn't go to a known thing, you drop it on the floor, and the northbound app will actually send it to the system administrator saying so-and-so's machine, I think, has this wacko thing in it.
So is that typical topology network?
Yeah, that's one of many different ways to do it. I just made this one. I mean, where I worked, we did something like this.
Is that the router on top of it? Is that the router?
Yeah, the internet, the thing going out to that's your external router that will route to the internet. Because all of this, OpenFlow is layer 2, is how they're doing stuff. Okay, so we're going to show, some bad, host 1.1 accidentally made a boo-boo, and they've got some bad software. Maybe they do it with their thumb drive. But with enhanced IP, they go to a port that is enhanced IP. So now the network address, that when it's expanded out, you'll see as the DNS entry is host11.jerknet, some name is the company, .biz, okay? And where I was at, I used jerk, but they didn't say, that's so unprofessional. So I had to instead use jeopardized, unsafe, risky communications instead of jerk. And I got away with it. So anyway, the thing is now, if it goes to your network, I might say, if it's from JerkNet, are you kidding me? Get out of here. You don't even deal with it. So I've warned everybody. And then let's say, though, I'm a Fortune 500 company, but I know that you're using enhanced IP. I go, well, he's probably cleaned it up. If it's coming to me, it's probably good. And so now I have another choice. If I know he's good, I'll say, okay, he's going to take care of that, but this is probably good information, or I'm just not going to deal with this until it's cleaned up. Your choice. So that's how you deal with bad malware detection. And let's say, okay, how does the whole thing work? Let's say another guy comes out here. See, now here would be new traffic, and it goes to the malware detector, northbound app. Then the northbound app says, whoa, this is bad stuff. And then the OpenFlow controller will then notify all of the other switches, anything that looks like this, whatever you choose. Send it out, drop it, send it to the enhanced IP malware detect net. Okay, now same thing with an elephant flow. Do you want me to go through this? Because it's going to be the same thing. And I've actually implemented this. This is really cool. That's the easiest thing to determine. Okay, all you do is look at the output. Let's say you have a 10 gig connection, and you look at the output. And if that particular port, and see, this information is available right at the switch. So if the switch sees 2 gigabits, 3 gigabytes per second, or gigabits per second, it says, whoa, elephant flow. And then it will adapt the whole network and then go to the tsunami net. I used to like that. They originally called them data tsunamis. I like that a lot better than elephant flows, but everyone's saying elephant flows now. So you send it to tsunami net. And so the DNS entry will say this is a tsunami. What it will also do, it will throttle it down. If you've only paid for 10 gigabits, it'll throttle it down to 1 because you don't want to DOS yourself. The incoming port will say, whoa, this is a tsunami. Maybe they'll allow 10. Maybe they'll allow 100 megabits per second. They can, and no one is touching the network. It's automatically grooming your network. Now the next one, we'll get to the VoIP. Okay, this is just showing how it works. Yeah, he notices and it comes up. Yeah. Okay. And then he comes out and he gets a new name, so it's Tsunami Net, or whatever you want to call it. Same thing with the VoIP. VoIP is pretty easy because you look at the TCP port, boom. And here's the other cool thing. TCP has what's called a 5-tuple. It's all it's interested in. It's interested in the source address, destination address, port number, and then I forget what the other two are, but it's only 5. OpenFlow allows you to look at 20 things simultaneously. So you can even look at a person's name, stick it in there. But the nice thing is, all I need is the port number for VoIP. All I need is a port number for data conferencing. Now what I do, once I see it's a VoIP call, let's see, we're doing the same, oh shoot. Oh, I just paused it? Darn. Anyway, what you do there is you send it to an enhanced IP port. That enhanced IP port, now you as the traffic engine, you as the ISP or as the network engineer, you choose what you want to do. What would I recommend? If you have the ability, stick it on its own wavelength. Okay, you don't have that kind of money, put it on VLAN. Basically what you're going to do is now really utilize properly the outbound traffic. If you want to do something with, and again, because it's OpenFlow, you pick the port that it's coming out. You choose whatever you want to do in order to pull that off.